your screen. And now, Margot Anjon, the floor is yours. Thank you.
Thank you, Fernando.
Hello.
So hello everyone. So my name is Jean Le Benray, and I'm here with Margot, my colleague. So we are working at EOMYS Engineering, and we are going to make this webinar on noise and vibration in electrical machines. So first, I'm going to briefly introduce the company in which we are working. So it's a company based in France, and we are doing engineering consultancy and applied research in electrical machines. So we have a team of R&D engineers who have different specialties, but two specialties are represented, which are electrical engineering and vibro-acoustics. So that's why we are doing this webinar. And we work a lot abroad. In terms of services, we do problem solving and diagnostic. So, but the special thing about the company is that we do both simulation and measurements. So we have our own measurement equipment for noise and vibration, so we can come and do field measurements to understand what is happening and give some solutions. We can also do design optimization of electrical systems, and we also provide some technical trainings focusing on noise and vibration. Finally, we developed and distribute simulation software that is called Manatee. I'll discuss a bit more about it in the next slide, which is dedicated for the simulation of electrical machines, so electromagnetics and noise and vibration due to Maxwell forces. So we work basically both at the design stage of electrical machines, but also after manufacturing of electrical machines. So let me start with the webinar. So we are going to make a short review of all noise and vibration sources in electrical machines, so not only electromagnetic sources. We'll see aerodynamic and also mechanical noise sources. In terms of physical origin, in terms of frequency content, and in terms of mitigation techniques. And then we'll focus more on the magnetic noise and vibration sources, and we'll see how we'll review also the noise control techniques, so how to reduce magnetic noise and vibrations, and we'll review also what kind of models do we have and how to make the simulation of this type of noise and vibration. So first I will let my colleague, I know maybe not, I will continue this part, not yet. So first let's see why is it important to include noise and vibration when designing electrical machines. First we can see one trend. It is the one that when you want to optimize the cost of your electrical machine, you will try to reduce the yoke thickness to decrease the cost and the weight also in application where the weight is important. And when you do so, you lower the stiffness of the yoke, and so you increase vibration and potentially the acoustic noise levels. A second thing, it's about skewing, because skewing is used a lot, but sometimes it's applied to reduce the noise, but it degrades the torque and efficiency. And we will see that there are many other techniques which can reduce noise due to magnetic forces. So we think that we can avoid skewing. And another thing about electrical machine design and noise and vibration, it's about the new topologies. We have now some special topologies with higher NVH challenges when you think about concentrated winding permanent magnet synchronous machine. So they introduce a lot of harmonics, special harmonics due to the armature field, and it creates specific noise and vibration issues. And you have also another topology that is very challenging. It's the brushless doubly fed induction machine. And at the end, of course, when you solve a noise and vibration issue after manufacturing, it means additional costs, weight, and project delays. It can also lead to thermal issues, because if you have to add an acoustic enclosure to lower the noise, then you also penalize the heat transfer of the machine. So it's really important, independently of the standards and requirements of your clients. We think it's important to integrate noise and vibration at the early design stage. Especially even if you fit with all the client requirements, a lot of issues that we have is just that the client thinks that the machine is too noisy, and then you have to do something. Okay, so in terms of noise sources, so here you have an example of the noise spectrum of an electrical machine, which is actually a traction machine, and I cannot make you hear the noise here, but we have some. If you go on our website, you can find some videos where you can hear these different sounds. But the idea of this slide is to decompose the noise, global noise level of the machine in terms of mechanical noise, aerodynamic noise, and electromagnetic noise. So first, mechanical noise is due, for instance, to bearings, and you can see here in this graph that it's a rather low frequency excitation that is increasing with speed. So the magnitude of the noise is the color, so in red it's high noise. In the middle you have the effect of aerodynamic sources, and it's characterized by a rather broadband spectrum, and it also increases with speed. And at the end you have electromagnetic noise. So it's very special because it occurs at very specific frequencies, so it's very high. It has a high harmonic content, and it's characterized by strong tonalities. So now I will let my colleague Margot talk about mechanical and aerodynamic noise sources.
Thank you, Jean. So the contributors to mechanical noise, are bearings, shaft imbalance, and eccentricity. Sliding contact between several parts of the motor, for instance, rotor and bearings due to shaft eccentricity or imbalance. Friction noises due to sliding contacts in slip rings or motor brushes are also contributors to mechanical noise. If the electric motor is coupled to a gearbox, gear noise would be a contributor to mechanical noise also. Furthermore, tightening fault can induce ripple noise, which corresponds to mechanical noise. But in this webinar, we will focus on bearing noise, for example, due to shaft imbalance and eccentricity. We will also talk about friction noise due to sliding between rotor bearings, and that could be induced by imbalance and eccentricity. To understand bearing noise, here is a review of existing bearings and causes of noise in each type of bearings. For journal and sleeve bearings, the roughness of sliding surfaces, lubrication, and manufacturing faults could be at the origin of bearing noise. In fluid bearings, as floating or oil film bearings, the instability of oil film in bearing induce additional vibrations of the rotor, as you can see on the figure on the right. And then it will induce noise. The oil film instability is caused by imbalance and eccentricity of the shaft. In ball or roller bearings, several causes are at the origin of noise and vibration. For example, manufacturing faults of balls or rings, which can induce waviness. Also, the presence of dirt or lubrication fault inside bearings. The resonance of the outer ring at its natural frequency, represented here on the right, bottom right of the slide. So you can see natural frequencies with the radial and axial mode shapes of the ring, and this can contribute to mechanical noise. Finally, the alignment fault or shaft resonances at critical speeds can induce a load difference on balls, as you can see on on the figure in the middle, and it can provoke additional vibration and noise. Of course, the noise emitted also depends on the running speed, the load of the electrical machine, the temperature, and as I already said, the alignment fault. Making an experimental measurement of the electrical machine, we will see how to recognize each phenomenon listed before, studying the frequency content of the vibration signal. For flow-induced vibration due to instability of oil film in bearings caused by shaft imbalance, the vibration signal is plotted in a waterfall diagram here on the right. That is a function of rotor speed versus frequency. The imbalance is observed as the first-order harmonics, and the instability appears at subsynchronous harmonics depending on rotor speed and critical speeds. As already said, if there is imbalance in a system, the first-order harmonic is observed in the vibration signal. For misalignment, both first and second-order harmonics are observed. Then for contact rub between rotor and bearings, for example, subsynchronous harmonics of half-order and first-order harmonics are observed in the vibration signal. The frequency content of bearing noise can be easily calculated if the noise is due to structural fault. Indeed, the frequency of the noise is linked to the rotational speed, the number of balls, and both their size and the ring's size. The noise induced by handling, that is, introducing dirt or breaking some parts of the ball bearings, will be changed in time domain, and sort of impacts will be heard. In case of flow noise, the signal becomes periodic. On the right bottom figure, you can observe the sound pressure level measured versus frequency. So it's sound pressure level for race noise versus frequency and as a function of speed. Higher is the speed, higher is the sound induced by rolling noise. In order to reduce noise induced in bearings, some solutions are proposed here. Among all the solutions listed, we can talk about application of elastic damping elements in bearing housing, as you can see on the pictures. Now I will talk about, I talked about mechanical noise, now I will talk about aerodynamic noise in electrical machine. One of the origin of aerodynamic noise and vibration is the airflow when the electrical machine is running at high speed. Actually, the machine acts as a centrifugal fan. The noise from cooling system is also at the origin of the aerodynamic noise. There exist three kinds of cooling systems which have been discussed yesterday in another webinar made by our colleague Pierre-Olivier Jandot. So these three kinds of cooling system in electrical machines are air cooling, water cooling, and oil cooling. In the case of air cooling, the fan is either fixed to the electrical machine and then rotating with it, or rotating independently. For water and oil cooling, an external pump is used, and fluid flow interaction with obstacles contribute to aerodynamic noise. There are three mechanisms of flow noise generation. The first one is called monopolar noise and is harmonic noise. It's due to quick variations of flow rate imposed by obstacles in flow. The contribution of this noise to aerodynamic noise occurs at high rotational speed. The second mechanism is called the dipolar noise and corresponds to either a harmonic noise or broadband noise depending on periodicity of the load. Is due to load fluctuation imposed by the fluid on obstacles. The third and last mechanism is named the quadrupolar noise and refers to a broadband noise. It's directly generated inside the flow due to shear strains induced by turbulences in the fluid. For air cooling systems, the fan noise characteristic frequencies can be calculated knowing the airstream velocity, the fan diameter, its rotation speed, and the number of blades. In the case that the machine is cooled with air passing through rotor ducts, the characteristic frequency of the noise is known thanks to rotor slots number and rotation speed information. Among the aerodynamic noise mitigation techniques, we can mention the blade geometry changing, the use of unevenly spaced fan blades, and the use of texturing on the blades. So now I will let my colleague continue the webinar. Thank you.
So now we are going to see, to focus on noise and vibration due to magnetic forces. So what happens is that we have some dynamic magnetic forces which apply to active materials such as lamination, magnets, or windings inside electrical machines. And generally we make the distinction between two types of magnetic forces, magnetostrictive forces and Maxwell forces. So we assume that magnetostriction can be neglected. That is based from our experience. We have analyzed many electrical machines during our consulting work, and we never had to explain any noise issue with magnetostriction. Maxwell forces, they, to summarize the effect, they tend to bring the stator closer to the rotor, following the law of minimum reluctance, magnetic reluctance, and the law of maximum flux. So this is a small experimental setup that you can watch the full video on our website. The principle is that we wanted to really make a visualization of vibration due to magnetic forces. So we have taken a very simple cylinder made of ferromagnetic material, which is like a slotless stator, and we have just applied a magnetic field with one pole magnet, so north and a south pole. And you can see that actually the cylinder is ovorized due to the magnetic field and the resulting Maxwell stress. This type of deflection are exactly what happens in electrical machines, and you only need a few micrometers of deflections to have a very high acoustic noise at high frequency. On the right, actually, you can see also a figure on how magnetic forces apply, how magnetostriction applies, and how Maxwell forces apply. You can see that magnetostriction acts inside the material itself, and Maxwell forces are concentrated at the interface between the iron and the air. And here that's the case of an induction machine, and in induction machine it's mainly radial forces. So Maxwell forces are dynamic forces because they include some harmonics, and this variation of field and of magnetic forces can be due to slotting effect, so some pole slot interaction in the field. It can be also due to time harmonics inside the current excitation, so it can be pulse width modulation. It can also be due to saturation that will change the shape of the air gap flux and then the resulting magnetic forces, but it can also be winding or eccentricity harmonics. That's an example on the top right corner. You have a simulation of the noise at variable speed, and that's made with Manatee software, and you can see the effect of different harmonics. So it can be harmonics coming from the stator field, rotor field, or special harmonics due to the winding, and you can see that basically some of the resonance are due to certain harmonics and some other resonances are due to other harmonics. So in terms of resonance, the resonance is an amplification of vibration and also acoustic noise due to a match between the force and structural mode of the stator or the rotor, it depends. Here we have illustrated a match between a stator mode, which is an elliptical shape structural mode, and magnetic force wave. And when these both match, when these shapes match in space and in time, we have this resonance effect. In terms of frequency content, it's more complex to characterize what is happening, because as we have this resonance phenomena which depends on the frequency on the force, but also on the spatial distribution of the force. And to characterize this spatial distribution, we call that a wave number. So it's a kind of spatial frequency. You can see the example here of a wave number 0. So it means that it's a direct, the DC component of the force along the air gap. Then you have wave number 1, wave number 2, etc. So if you want to characterize the spectrum, you have to speak both in terms of frequency and wave numbers. And what is interesting also with this wave number is that the lowest wave numbers give the highest vibration due to the lower yoke stiffness. So when you consider very high frequency variation of the forces along the air gap, the structure will be too stiff to vibrate under this type of excitation, so you can neglect this type of excitations. So if we want to take two examples in terms of spectrum, two-dimensional spectrum of magnetic forces, we have one example on induction machine and one example on permanent magnet synchronous machine. F slot is the frequency due to slotting effect, so in induction machine, and you can see that it's proportional to Fs, which is the fundamental electrical frequency, and then you have the number of rotor bars, Zr, divided by the number of pole pairs, P, and you have the slip that is involved. So this first frequency is actually the rotor slot passing frequency, but this rotor slot passing frequency can be modulated by plus or minus 2 times the electrical frequency. And the resulting, the associated wave number at this particular frequency is given by a combination between number of rotor slots, number of stator slots, and number of pole pairs. So for instance, if you take this machine with 36 stator slots and 28 rotor poles and 3 pole pairs, you obtain an excitation of wave number 2, if you do the calculation. And it means it's rather low wave numbers, so you can have vibration and noise issues in this particular case. Now, if you take the example of permanent magnet synchronous machine, there are some similarities. If you want to get the wave number R slot due to pole and slot, so rotor poles and stator slot interactions, it is also given by a combination of stator slots and pole numbers, but you don't have the rotor slot number that is involved in the expression, and you can show mathematically that actually the lowest wave number is given by the greatest common divider between stator slot number and pole pairs number. So this is a small example with a 12-slot 10-pole machine, and you can find that the greatest common divider is actually 2, and it's obtained with this integer u equal 1, which makes the excitation of wave number 2 occurring at twice the electrical frequency. But you can see that with this expression, you can find some other magnetic forces, such as, for instance, 2 is also equal to 70 minus 72. So U equals 7 gives another force at the same wave number at higher frequency, which is here 14 times the electrical frequency. Actually, we can show that in open circuit condition for permanent magnet synchronous machine, this two-dimensional spectrum can be represented like this. So each point is a harmonic force that is occurring, and we can show that the frequency spacing of these forces is linked to the least common multiple between the stator slot and the pole pair numbers, whereas the frequency spacing but along the air gap, so the wave number spacing, is given by the GCD. And you can find actually that the very special wave numbers 0 Wave number 0 is a pulsing force, and if you take the one occurring in tangential direction, it's the cogging torque. So you can find in this graph, you can find the well-known result that the cogging torque frequency is given by the least common multiple between stator slot and pole pair numbers times rotational frequency. So now we are going to review a bit the transfer path analysis of noise and vibrations. You can see here a schematic of an electrical machine. What is important to see is that we have two main paths. We have what we call airborne noise, so it will be direct vibration of the air going to the ear, and you have what we call structural borne noise, which is noise that is not primarily created by the part in vibration that is vibrating, but first the vibration will propagate to another component that will be able to radiate acoustic noise. So here you have this table which summarizes the different paths. For instance, you have the direct path of stator yoke. That's the first line. If you take a wave number, positive wave number, you can create radial deflection of the yoke, and it will create direct airborne noise. And another one, which is interesting, is the third line. It's, for instance, cogging torque. So it's a pulsing force. Itself, it cannot generate noise, but if you consider structural borne vibration, it can create noise. What time is it? I have to speed up. So in terms of noise, magnetic noise mitigation, so the general rules are to avoid these resonances, which are very harmful between magnetic forces and structural modes. And for that, the simulation is recommended. Even if you can do hand calculation, as we have shown before, it may be complex because there are many harmonic waves involved in the air gap. On the top right, you can see an illustration of the effect of changing the rotor slot number of an induction machine and the effect on noise. And you can see that there are like up to 20 dB change just when you change from 80 to 78 rotor slot number. So there's a huge effect when you change the rotor slot number because it both changes frequencies and wave numbers of exciting forces. Then as general rule, you have also to reduce asymmetries because a lot of machines which are supposed to be quiet on the paper, we could say, when you manufacture them, they can be noisy due to asymmetries such as eccentricities. It can be also variation on magnet position or on the lamination roundness. So at the bottom you can see the example also in Manatee software of the effect of the roundness of a stator. On the left you have perfect stator noise as a function of speed. On the right you can see that if you introduce an asymmetry of the stator bore radius, you completely change the noise and vibration behavior. Then we have a lot of actions to take at the electromagnetic design stage because we can apply skewing, pole shaping, we can modulate the pole or slot position or width, doing spread spectrum strategies as we can apply also for blades to lower the aerodynamic noise. We can also apply notches or flux barriers. So there are many different options. In terms of control, we can also work on the techniques such as the spread spectrum switching strategies, so to avoid that the switching frequency is creating forces always at the same frequency. We can play on this. We can also inject some harmonic currents to create new forces that will damp vibration and noise. And in terms of structural actions, we can play on the lamination geometry, we can play on the damping. That's extremely important to optimize the damping in the machine by choosing the right resin, for instance. And you have also some other ideas such as playing on the coupling between the housing and the lamination, or using what we call structural spacers. In terms of modeling and simulation, so one good thing is that we can assume that there's a weak coupling between electromagnetics and structural mechanics. So the deflection, the very small deflection of the yoke creating noise can be assumed to not to change the electromagnetics. So we have to have an electrical and electromagnetic models to calculate the field, and then a structural model and an acoustic model. For each of these models, we have different options from analytical to numerical, going through semi-analytical techniques. Of course, analytical will be fast and less accurate compared to numerical method, which is slow and more accurate. And here what we recommend is actually to make some kind of hybridation between methods. So sometimes using semi-analytical techniques and sometimes analytical techniques, especially in the early electromagnetic design phase. So here is a small review of the existing software for the evaluation of vibration due to magnetic forces. So I'm not going to review each line of this table. You can see that all the electromagnetic software now propose a coupling to estimate noise, to estimate vibration at least due to magnetic forces. One interesting thing is that it means that it's really important now for the electrical machine designers to be able to estimate vibration due to magnetic forces. And we can notice also that they only offer a direct coupling approach, so it means they can offer the possibility to directly map electromagnetic forces on a structural mesh. And one other thing is that even the multiphysics software suites like COMSOL or ANSYS Workbench, they don't really give ready-to-use multiphysics simulation workflows. You still have to connect some box and do some work to have at the end the evaluation of vibration and noise due to magnetic forces. So today we think that we propose the only software to have the following features: to first to have an indirect coupling approach. That's what we call electromagnetic vibration synthesis, to speed up the simulation time. And we also propose semi-analytical models to have a tool that you can use during the early design phase when you wonder what is the difference between this slot pole combination and this other combination in terms of magnetic noise and vibration. We can do the calculation with Manatee in a few seconds. And we also, our tool propose an integrated multiphysics simulation process, so you don't have to define how to couple the physics. One important thing also is to remind that the fully numerical approaches have some limitations. First, in terms of calculation time. If you want to include skewing, if you want to include variable speed application, if you want to include pulse width modulation up to 10 kilohertz, you will not be able to do that in fully numerical software. We also have some issues due to remeshing ripples sometimes, and you have, in some cases, you have spurious interharmonics that come into the sound spectrum, so that you don't have the right sound power level at the end. So, as I told you, we recommend to use semi-analytical models. So what do we mean exactly by semi-analytical models is, for instance, for electromagnetics, what we call subdomain modeling techniques. And if you talk about structural mechanics, it would be work modeling the stator as an equivalent cylinder. And this allows you to calculate the noise at variable speed in a very short calculation time. You can see here the electromagnetic results of subdomain models, and you can see that either for a synchronous or an induction machine. And you can see that we have very good results compared to finite elements. We have all the harmonics right, with the right magnitude, and the calculation time is extremely small. It's a fraction of a second for the full air gap flux distribution, including all time and space harmonics. And at the end, of course, we cannot only do semi-analytical modeling, so at the end, we recommend to use finite element models when you have a detailed CAD model of the housing and everything around the electrical machine. But then we recommend to use electromagnetic vibration synthesis to accelerate the simulation time. Here we have the example of this technique used in Manatee software. So Manatee is actually coupled to some finite element software for electromagnetics or for structural mechanics. For structural mechanics, for instance, we have a coupling with OptiStruct. The idea of this algorithm is not to apply directly forces on the structural model, but to separate the characterization of the structural model and the characterization of the operational excitation. And at the bottom, you will see what happens. We know that due to the slot combination and due to the special winding that you choose, that the forces will have some particular wave numbers. For instance, they will not have, you will not have wave numbers 3 or 7 or whatever. Maybe you will have only wave number 0, wave number 8, etc. So it means that the magnetic forces have a very special distribution along the air gap. So we apply these special patterns on the structural model, and we do harmonic analysis to vary the frequency. And then we obtain some structural frequency response function for each of these wave number, and we store that in the database. And then, assuming that the model is linear, so the structural model is linear, which is a good assumption, we can just do the summation of all the forces to get the overall vibration. And it means that we can do a torque speed curve very easily, because we don't recalculate at every new current or voltage the structural mechanics. The structural mechanics have been only computed once, and then you can do all the loading, the change in terms of electromagnetic loading that you want. So this is an example of what we can obtain with semi-analytical models of Manatee simulation software. On the left, you have the test obtained for the sound pressure level of two different machines, machine A and machine B. And on the right, you have the results with Manatee. You can see that machine A has actually two very strong resonances here. And these two strong resonances are correctly captured by Manatee software. Of course, we have some errors on the absolute value of the noise level, but what is important here is to give a tool that will help you to see that there's an issue in your current design. And this is only 10 seconds of calculation, and you already know that there's an issue on motor A. And when switching to motor B, you can see that in Manatee, basically you cancel the magnetic noise because it's less than 60 dB. And if magnetic noise is very low, it means that mechanical and aerodynamic noise will be the dominant sources, and that's what happened in this case. We can see that motor B is the noise is around 75 dB. Which is typical of a value due to mechanical and aerodynamic noise. So here we can show, we have shown that even if you do strong assumption, if you neglect saturation, and that's a traction machine, so there's a lot of saturation, even if you neglect saturation and assume that the stator is a simple cylinder, you can do good things and avoid a noisy machine at the electromagnetic design stage. So to conclude this webinar, I want to emphasize on a few conclusions. First, skewing is not the only technique to lower the noise, and actually skewing is not easy, because sometimes the optimal skew is not necessarily one slot pitch, and the skewing also depends on the load conditions. And okay, so skewing is not an easy technique to implement, and there are many other techniques, and so you can maybe increase the efficiency of your machine by removing the skew, but using notches, for instance, or doing some other techniques. Then the second message, of course, is that magnetic noise and vibration can and should be considered at the early electromagnetic design stage. You can avoid some strong resonances when you choose the overall dimension of your lamination, the slot pole combination, and stuff like that. And then we can do numerical calculation acceleration using some algorithm like electromagnetic vibration synthesis. And at the end, you should always use experiments if you want to improve the simulation process in terms of absolute accuracy. You have to make the difference between if you want to have a simulation model that is accurate in terms of relative value or absolute value. And the absolute value of noise and vibration will always depend, for instance, on the model damping. So we have, in our simulation software, we have some default values coming from our experience, but model damping will depend on the specific manufacturing process. So you should update everything regarding this. So that's all. So thank you for your attention, and we look forward to your questions.